was just a decimal. Did you put it in the side carets like you should have? All right. You guys agree? 3 decimal places, rounded, truncated, and then? Okay. So that's our acceleration vector, which we could talk about. The rate of the rate, right? Isn't the horizontal rate increasing at a rate of? Yeah. So the horizontal velocity is increasing at a rate of, and the vertical velocity is decreasing at a rate of. We could talk about things like that. We can even talk about concavity, but could we? Because aren't these individually just talking about how fast horizontally, how fast vertically? To do concavity, wouldn't we have to find the second derivative? Okay, this one, letter B, vertical tangent line, what'd you guys get? T equals? And there was only one? Okay, letter C. How easy, hard? What did you guys do in contemplating what was going on as you took the limit of y prime over x prime? Oops, that's awkward. Equals. So you just looked at the functions? So then degree bottom wins. So therefore, what if it was 0 over 0? Because you have e to the negative t, and e to the negative t would be over e to the t. And so over bottom wins. So that whole thing is 0. So it's sine inverse of 1. Sine is 1 at not 0. Does that make sense? So it's going to be pi over 2. But either way, you can go ahead and be like, oh, hey, that would be 0. Sine inverse of 1 is pi over 2. Sweet. 0 over a number. Yeah. Equal to 0. Does that make sense, everybody? And that was just degree tests. Now, could you have graphed y3 to be y2 over y1? And then look to infinity, I suppose. But think about that window and how nasty that would be, right? Like, okay, letter D. So what have we thought about so far? The graph of the curve has a horizontal asymptote at y equals c. The graph of the curve has a horizontal asymptote at y equals c. Write but do not evaluate an expression involving improper integral that represents this value. What's Maggie thinking? She's thinking tangent line, and she's thinking like an integral is net change sort of thing, like a 0 to x, but she's going from 0 to c. What's the struggle in letter D? Like, what do we wish it was saying? This value meaning c. They want you to solve for c somehow. Now it says an improper integral. Why is that a struggle? Either to infinity or to a vertical asymptote, right? Improper integrals, one of the bounds has a problem. So first of all, does c have a problem? If it was a vertical asymptote, yes, but horizontal asymptotes, are curves allowed to cross horizontal asymptotes? Yes, and careful. Is C an x bound or a y bound? It's not even like a t. So we couldn't use C as a bound anyway, just because he's not even a t value, so he's not a t bound that gets plugged in. Okay, so hold on. Why does Aryan's idea of infinity sound smart? It's a horizontal asymptote, and integrals go back to originals. I think, Riley, you were saying that earlier as far as like integration is net change, thinking like with this clue. Ooh, with that clue. What are we trying to integrate? What are we trying to think about? I don't know if area under the curve is necessarily where our brains are supposed to be thinking. What's everything in terms of is t, right? Could we eliminate the parameter? No. Because eliminate the parameter, we have to get back to x equals, we have to get back to y equals, then we have to solve the x equals for t, and then we have to plug in, we're not eliminating the parameter, so who do we have to be in terms of? Time. So for in terms of time, we're going from 0 to infinity, we're trying to plug in time. So time is going to infinity. As time goes to infinity from 0, because t is greater than or equal to 0, who or which values are we caring about? Who do we need to solve for? C, y values. So who are we looking at? Y prime. So can't we plug in y prime? And if we plug in y prime, we could just name it what? dy dt. Don't name it dy dt. That's disgusting. Just plug it in. dy dt is so improper with notation, right? So if we integrate oh, is that why it was going wrong? Yeah, we talked about cube. I think you guys were powwowing. If we plug in y prime, we're going back to y. We're going from 0 to infinity trying to think of, okay, this thing is getting closer and closer and closer to a particular y. Hold on. Wait a minute. Why would it make sense that I say c equals -3 plus? Integration is net change. But wait a minute, integration is net change. I need an f of b equals f of a plus, right? Why is he my f of b? F of b minus f of a. Who's my initial? Who's my infinite? Yes or no?
Since that point, 6 -3 times t equals 2, shouldn't you start from 2 then?
Oh, I wasn't even watching. Yeah, good. Because I need to start somewhere initial. Because I don't know where it is at 0 at all. Nope, I have no clue. Okay, now is it appropriate? And if you're wondering, now this is horrible notation, you should never write this, but you could do something like, I know, right? We're not writing that. But, does that make sense? I throw in my y prime, I get out my y of infinity, and we should put like a t in the limit as t goes to infinity, and that should be a t going to infinity with a limit and blah, blah, blah. They say we're allowed to write an improper integral, so I'm just throwing it in and leaving it there. But won't this get me a limit as t goes to infinity of the antiderivative minus the antiderivative of 2, and then those are going to cancel, and then those are going to equal? That's why I'm allowed to put c in that spot. Kathy? B and C? This one? No. Oh, sorry, D and C? F of infinity is us thinking about the y value as we head to infinity. So it should be the limit as t goes to infinity of f of t equals c. That's the proper way of writing it, and that's technically how we would rewrite this integral. So maybe it's a little bit easier for us to think about it this way, ending in, because I could do the limit as t goes to infinity of f of t is equal to f of 2 plus the limit as b goes to infinity of 2 to b of f prime of t. And then I can rewrite this to be the improper integral 2 to infinity of f prime of t dt. And then that's -3, and then that's c, if that makes more sense. The other way that I'm thinking that you could have done this is, guys, what's happening if you have a horizontal graph is approaching? What's happening to the tangent line? As you go to a horizontal asymptote, what's happening to your tangent line? The slope is approaching. Oh, wait, we already knew that the slope is approaching 0, like it's leveling off. Well, if we could figure out where it's leveling off, like what it's leveling off to, but the problem is, does the slope of the tangent line tell me at all where I am? So even though this was great, and this tells me there's a horizontal asymptote because somehow this thing is leveling off to infinity, well, if it's leveling off, it has to be approaching some horizontal line, right? This tells me there's a horizontal asymptote, but this would never get me to C. This just tells me it's leveling off somewhere. I have to actually dig into the y, and the y prime specifically, in order to figure out the y value of the horizontal asymptote. So they're related, Kathy, you're totally right. But this one's just saying there is a horizontal asymptote, there is leveling off, whereas this one says where it's leveling off to. Does that make sense? Okay. So was it quite as straightforward as we thought yesterday? Maybe in some ways yes, maybe in some ways no, but are we okay in our calculators? Like, did you guys use y1s, y2s, you used your n derives, you could have used your integration feature if we needed to. Well, how would you go to infinity? Good thing we're not doing that. Yeah.
Just about calculators. You always mentioned like you can use your y1 and then like y3 you can put y1. How do you get that y1?
Can't you use the shortcut of second window, second trace? Sorry, alpha. Alpha trace, I think. There you go.
Oh.
But once you get up here, you can do like alpha, and you can just use any of those. Yeah. Does anybody else not know that alpha trace gets to y1s, y2s, y3s? Alpha y equals gets to that nice little fraction, and alpha trace, like alpha, there's an alpha hidden menu for each of those as long as your calculator is updated. And if your calculator is not updated, we should get it updated. Pause. Everyone, I want you to turn on your calculator. I want you to hit alpha y equals and have it face me. I don't trust you all. I love you all, but I just don't trust you. Have it facing me. Alpha y equals C. It's upgraded. Yeah, alpha y equals and have it face me. Good. Good. Okay, everybody's updated? Okay. Alpha y equals, there's hidden menus that we use a lot. Yeah. So alpha y equals, we can do that cool little fraction-y thing. Or we can do like all of our y1s, y2s. Yeah, that's what I was worried about. You can do n derive, you can do integrate. Okay, you guys see the hidden menus, right? Like I don't just talk about them in class and we ignore them. They save time. Some of you have totally never seen this before. Okay, love you all. Now you know calculators are a thing on the AP, true? All right, section 11.3. Homework on 11.2 is due tomorrow. Homework on 11.2 is due tomorrow. I had it up here at the beginning of class. If you guys weren't here, they were just writing it down. I mean, you can take a picture of it, but it's on Google Classroom. And, yeah, we'll get there. Right? We'll get there. Okay, tomorrow. CalcBC has their areas and volumes test tomorrow, so the more help, the better. Guys, please, 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 please. Them seeing you do it and being like, I get it. They don't get it. They can see it, they can understand it, but them getting it is them being able to do it on their own with a problem without a picture, right? Now, don't force them to do some ridiculously hard integral that I wouldn't make them do by hand. Like, they do need to use their calculator too. But please have them start with a picture, have them shade the region, have them show the axis of revolution if it is one. If it's a cross-section, we know it just pops out. Please force them to do the painful work of, I'm stuck. And be like, okay, what's your forever card? Okay, what's the direction say? Okay, is it being rotated or revolved? I had a kid who's usually like pretty confident and came to me with a problem this morning and said, I don't understand the directions. I'm like, you don't understand that? Okay, read me the directions. Following the volume of the solid sliced perpendicular to the x-axis, it's just pi radius squared, right? I'm like, do you read anything that says revolved or rotated or circle? I was like, did you read the second sentence? I didn't actually say that, but I was like his group member. I was like, read the second sentence. Cross sections that are squares. I'm like, how'd you get pi r squared? Like they're not thinking. To some extent. It's overwhelming your first time, right? It's overwhelming your second time. Yeah. And that's okay. You just need to tell them, like, it's English. Read the English. See the square and not the circle. Like, I don't know. And he's a confident one. Anyway. It's okay. Like, they know it. They just, I don't know, whatever's going on in their minds. No. It's not.
I was going to say.
No. No, like they get it. Like even the ones like Aryan was talking about one he was helping, and I was like, this morning she was totally like, I don't know any of the revolving rotating. I'm like, well, you did the whole practice test and you say you understood it. You should know revolving rotating. Just slow down. You need a whiteboard. Make a picture. Shade it. Like they just need to. Yeah. And they don't have to do the whole 3D thing. Hey, pictures help. Why am I making a big deal about this? Because my AB kids need tutoring? Yes, but also, guess what we're going to work on? Pictures help. Carrie's face. I'm going back, Carrie. I'm going back. It was just perfect. I was like, pictures help, and she was trying to get a picture, and all of a sudden she was like, it was just great timing. It was great timing. It was just because I went forward too much, but it was just the perfect expression for what I was saying. Why did I put a whole line through it? You already have it in your note. Didn't we already do polar? Well, I mean, you are going to need to use it, so it's up to you. Could you write it down and use it here and not have to flip back? Yes. Could you flip back? Yes. Could you do both? Yes. Go team. Polar curve. R equals F of theta. Yep. Going from polar to rectangular. It's okay, just quick review. We've already been here, but isn't X there and Y there and R is the radius? Ooh, do we remember this? And this is a theta. So X squared plus Y squared is R squared. X is equal to R cosine theta. Y is equal to R sine theta. Oh my goodness, it's like vectors because it's a right triangle. Tangent of theta is Y over X, and tangent inverse, just put it in the right quadrant. Okay, this you're going to need. Parametric, didn't you have to review a little bit too, eliminating the parameter? Okay, so what's going on this page? Oh, it keeps happening. Oh, because I zoomed in for the cube. That's why it's mad at me. All right, zoom out. What's going on here? Wait a minute. No. We have this. Well, some of you might need to write that. Well, we should already know that. We should have that down. Anyway, even though all of these are very easily forgotten, very basic formulas that we should have down, what are the ones that are new? They're not new, they're pre-cal. They're just ones that you've forgotten that we're going to need. Power reducing formulas. Power reducing formulas. Back in pre-cal, they seemed ridiculous. In CalcBC or Calc 2 in college, all of a sudden it's like, oh. Now, are we on 29? I think we're totally in a different place. We're on 30. Okay. The power reducing formulas. Now, could you technically just go back to the beginning and add them? Yes. But do some of you just need to make a trig card and be like, all right, I just need to memorize these? Yes. Power reducing formulas. Cosine squared is equal to, what is the big deal about a power reducing formula? Throw cosine squared into an integral, and what are you going to do? 1 over secant squared. Yeah, no, that's not going to help. It's in the denominator. Exactly. The only way to do it is with a power reducing formula, because if you go from here to here, oh, hey, 1/2, I can integrate, and oh, hey, 1/2 cosine of u, I can totally integrate. Can't, can. No, integration by parts. No. Can't, can. Cosine to the 4th, no big deal. It'd be cosine squared squared, this squared, and then power reducing formula. We go, oh yeah, it just keeps on going. If you have a single trig raised to a power with nothing else, secant cubed. Oh, that one's a party. It actually needs trig sub. Anyway, some Calc 3 people make them just memorize it. Yeah. Yeah, secant cubed is the big one that I've seen both at Santa Monica and at COC and at more part calculus classes. All of them use secant cubed. Kiddos, what are we going to do tomorrow? Graph polar. How are we going to graph polar? We need polar paper. Oh, we don't need polar paper. We just need to know how to find angles and how to go out radii. We're going to work on pictures tomorrow. Why? Because visualizing is important. So what are you going to teach AB kids when you talk to them? Pictures. Visualizing is important.